All right, let's try again because it's swiveling. Okay, now it's swiveling. All right, so just to recap where we were, Chebyshev's theorem, he proved that there exists an A and a B, 0 less than A, less than 1, less than B, less than infinity, such that A x over log x less than equal to pi of x, the number of primes at most x, less than equal to B x over log x. And he did this entirely elementarily, which is very nice. Now, of course, the prime number theorem is that A equals B equals 1. And so he got, A was a little bit over, I think, 0.9, B was a little bit less than 1.1, 1.2. If you do a little bit more work, you can get them closer and closer to 1, but he was not able to prove that they equaled 1. He might have been able to prove that if the limit exists, the limit is 1, but that was essentially where he was. So it's close. For a lot of applications, this is enough. And so I'll give you one application of this first, and then from that I will go and talk about how you would handle things related to the proof. So claim the sum of 1 over p diverges. So if there were only finitely many primes, what could you say about the sum? Converges. So unfortunately, this is the case that gives you no information. It turns out that the sum of the reciprocals of the twin primes converges. We talked about that in an earlier class. Unfortunately, we can't use that to deduce anything interesting about the infinitude of the twin primes. So how can you use Chebyshev to prove something like this? So I'm going to just sketch the argument, but how can you use this information to attack a problem like this, that the sum of the reciprocals of the primes converges? I'm sorry, diverges. Any thoughts? Not quite. So we only know things about the density of the primes. How would the integral test help us? Let's see, is 1 over p slowly changing or rapidly changing? Relatively slowly. So you can break the real line up, or you can break the integers up into large swaths where the function doesn't change that much. And this gives you a really good count in intervals. So in fact, you can use this to prove something called Bertrand's postulate. If x is large, there exists a prime in the interval x, 2x. Anybody know what large is? I'm using closed intervals, so. Yes. So as long as x is at least 1, there's a prime between x and 2x.
It's always 1 or 2.
Sometimes it's 3, but I mean 3 is huge, exactly. So if x is 1, this is going from 1 to 2. As long as x is less than 2, I include the prime 2. Once x hits 2, I still have that prime 2. So there's always a prime between x and 2x. The way you would prove this is you would look at pi of 2x minus pi of x. Okay, so if I'm going to do something like this, this is going to be greater than or equal to, I use a lower bound here, a 2x over the log of 2x minus b x over log of x. So if I do something like this, this would give me a lower bound for the number of primes, there we go, the number of primes in the interval x to 2x. Now, obviously, for this to be useful, I need some control over a and b. If a is very, very small and b is very, very large, this will be a negative number, and we will have something like this, at most negative x over log x primes in the interval. Well, while a true statement, it's useless. So you need a not too small, b not too large. And Chebyshev was able to get good enough values on A and B to prove a result like this. So how does this help us now? This is going to help us with dyadic decompositions. So we'll write the integers as the union n goes from 1 to infinity. Actually, probably should just do the natural numbers, not the integers. Of the interval 2 to the n, 2 to the n plus 1. And I'll include the left endpoint, but not the right. And if I want to show the sum of the reciprocals of the primes diverge, do I need to look at all of the integers, or can I start at some point onward? I can start at some point onward. A couple of finite values of integers is not going to affect the convergence or divergence. So I could start at some big N, so far that Chebyshev's inequality is holding. And now when I look at the sum, I want to try to figure out what's going on. So this seems to move. Okay, so I want to try to figure out what is the sum like. So consider 1 over p on the interval 2 to the n, 2 to the n plus 1. So we're going to sum it, and we'll call this interval maybe I sub n. So we'll sum p and I sub n. Do I care about a lower bound or an upper bound? Lower bound. Why do I want a lower bound? I want to show it's...
You want to show it's... Well, if you showed an upper bound, then you need... I mean, just kind of disproving what you want to prove.
No.
Well, not that, but...
No. What am I trying?
It doesn't really help to show an upper bound.
Correct. Right. If I show that the sum is at most positive infinity, this is not a good use of class time. Right? However, if I show the sum is at least positive infinity, you're now getting good bang for your buck. Right? So we want a lower bound. We could get an upper bound as well. How could I get a lower bound for this? Let's imagine the worst possible situation. What is the worst possible situation for us? But we know that can't be the case. The worst possible given Chebyshev. Chebyshev died for us. He proved this theorem for us. Yes.
That x is your prime every time.
I'm sorry?
That like x is your prime every time.
The
Lower edge of
the lower edge is our prime every single time. Should I really say the first prime is at 2n, the next prime is at 1 plus 2n, the next prime is at 2 plus 2n? Should I do that? The number of primes is so small that the amount I move is not going to really help me. Why not just assume all the primes at the extreme left endpoint? Is it possible every single prime could be at the extreme left endpoint? No. But it's going to make the analysis a lot easier. So we will have 2 to the n a prime with what multiplicity? So what's the smallest this sum could be? How many primes would I have at the extreme end? According to Chebyshev. So if we look, Chebyshev tells us there's A and B such that the number of primes... This doesn't seem to want to move today. Let's try moving in closer. All right, so that the number of primes is ax over log x is less than or equal to pi of x is less than or equal to bx over log x. So I'm trying to make the sum as small as possible. How many primes will I have to assume in my interval? Ax over log x, where x is going to be 2 to the n. So this has to be greater than or equal to a times 2 to the n over the log, I'm sorry. The number of primes is a, right, 2 to the n over log 2 to the n. And now I have to multiply by 1 over the prime. And the prime is 2 to the n. Right? So this is the number of primes, and I'm assuming the worst possible case for me, that each prime is exactly at 2 to the n. Well, if you notice, the 2 to the n's cancel. The log of 2 to the n is just 1 over n. So we get a over log 2 times 1 over n. And here I have a sum p and in of 1 over p. And so now if I just sum over all n, What do you know about this sum? It diverges. It's the harmonic sum. So we get that the sum of the reciprocals of the primes diverge. So this is an extremely common argument in analytic number theory, is if you have estimates of the density, you can pass from knowledge of the density to knowledge of certain sums, which is not surprising. This function 1 over p is changing so slowly in these intervals. How much does it change? It changes by a factor of 2. If I went to get the upper bound, all I would be doing is changing it by having an extra factor of 2 and replacing a with a b. Well, actually, wait a minute. I think we actually did things wrong. In terms of making this sum as small as possible, we don't want to put the primes at 2 to the n. Where do we want to put the primes? 2 to the n plus 1. Oh, no. Not a big deal, right? All that does is fine. We get an extra half. Not a big deal. I wish I could say that. I could say it was a little bit mistake, but it wasn't. It doesn't matter, though, and I can say that. Because the amount that they're going to change by is a factor of 2. It's a constant. It's not going to depend on n. It's not going to make any difference in the estimation that happens. OK, so this is, yes?
And that less, you know the sum is greater than or equal to the left-hand side because that's just plugging in 2 to the n of the a.
Well, this is a lower bound for the number of primes I have. And this is smaller or equal to all the primes that I have. So each prime over here is going to contribute more than this.
Yeah, I see.
And this is the number of primes I have. So this is going to be a really good, this is going to be a lower bound for that contribution.
I see. Could we have used the prime in x comma 2x? Are we using that right now?
No. Not, well, in some sense.
We're looking at a bunch of windows of x comma 2x. And
right.
say there's at least one in each one.
But we need more than just one, because if we only have one, we get a geometric series.
Yeah.
So this is worth highlighting, so I'm glad you asked this question. When we prove that there's a prime between x and 2x, the way we prove it is we prove there's a huge number of primes in the interval, therefore there's at least one prime. So if you actually look at this, you'll get that there's a positive constant times x over log x primes in the interval. So it's not just one prime, there's many primes. So we could actually do a little bit better over here. We could try to play games and say, well, how many primes do I have in this interval? So actually, I might have been a little bit careless here. So you might have actually caught me on something.
I think that would give you maybe more accurate, but if you're going for showing that diverges, it might be better to go for less accurate. If you're less accurate,
right.
You know, is the lower bound.
Well, let's think. Right, this is overestimating the number of primes greatly, because this is going to count a lot of primes before 2 to the n. But if I have extra primes like 2, 3, 5, 7, I'm now replacing them with the value at this point. So this is actually correct. You are right that in some sense a better estimate would have been to be like pi of 2 to the n plus 1 minus pi of 2 to the n divided by 2 to the n plus 1. That would be the number of primes in the interval times the smallest possible prime in that interval. That would be a more accurate estimate of what's going on. But we don't need that more accurate estimate. I can put in extra primes. And the reason is if you look at how many primes I have before 2 to the n and how many primes I have up to 2 to the n plus 1, they're going to differ by a multiplicative constant. They're on the same order of magnitude. So being careless over here is not going to hurt me. This is very different than we were trying to prove you could interchange the sum and the derivative, the infinite sum and the infinite derivative. There we had to be very careful with the technical arguments. Here, for arguments like this, I'm just looking for a lower bound. I'm not looking for the optimal lower bound. Now let's see though, did we make a mistake? Actually, I think you've convinced me now that this is not quite right. So why is this not quite right? Yes?
Should we be using b? That's the
it's not b, but this is wrong. So let's see why this is wrong. So this is a very good mistake to make. So let's draw it carefully. Here's 2 to the n. Here's 2 to the n plus 1. Here's everything before. I have some number of primes up to here. I have some number of primes up to here. And I have some number of primes then in this interval. If I'm using a 2 to the n over n plus 1, I'm just counting how many primes are in through here and using that as my count for the number of primes in here. I can't do that. I do have to use pi of 2n plus 1 minus pi of 2n. So what I need to do is I need to look at, let's do more carefully. I want to sum primes in the interval in 1 over p. This will be greater than or equal to the smallest possible prime in that interval times the number of primes in the interval. Right.
The number of couldn't you estimate the number of primes by saying that it's greater than or equal to the underestimate for the pi 2n plus 1 minus the overestimate for pi 2n?
Right. We need to use this.
Yeah.
It was too crude to just use the ax over log x. So that was a good comment. Make sure you email me. We need to say this is greater than or equal to 1 over 2n plus 1. And now we want to make sure that we underestimate the number of primes. Because if we overestimate the number of primes, that could force it to diverge because we're putting in too much stuff. Right? If we were trying to show it converged and we had an upper bound and we put in too much stuff, well, that's fine. If we put in too much stuff and it still converges, that's fine. If over here we need an underestimate, what's an underestimate for this? This would be a of 2 to the n over log 2 to the n minus b 2 to the n plus 1 over log 2 to the n plus 1. I'm sorry, I just switched. Yes, I switched it. Right. We want to use the underestimate on that side and then the overestimate on the other side. Yes, thank you. So now when we do it like this, this will give us a underestimate of the number of primes. And so there was a reason why I was writing this before going into the proof. And then I had forgotten why I had wanted to mention Bertrand's postulate first, is because we can't just do the simple estimate. So we need this to get a good estimate. Now what do we do over here? We need to show that this is approximately some constant times 2 to the n over log 2 to the n. And again, log of 2 to the n plus 1, log of 2 to the n, it's about log of 2 to the n. So this is just now some algebra. And now for this to work, we need some good control over a and b. If a is very small and b is very large, this is going to be a negative number. And we'll have the sum of the reciprocals of the primes is greater than or equal to negative 5. That will be useless. And so in the book, I go through the argument of how you can get a reasonable estimate for a and b and prove that there is a positive constant, c, such that the number of primes between x and 2x is cx over log x. And that's really what we need here. So this would then become greater than or equal to 1 over 2 to the n plus 1, c 2 to the n over log 2 to the n. And now the argument would proceed exactly as before, and this would be essentially some constant divided by n. So, well, it doesn't matter here, because for something like this, that's going to just change things by a constant. If you could call this n plus 1 if you want, or n. It's just going to change the constant c.
No, I meant instead of 2 to the n, wouldn't it just be 2?
No, because x is of size 2 to the n.
Okay.
Right? So the x, it's going to be some constant times x over log x. So this gives you an idea of what you can do with these density arguments. What about the sum of the reciprocals of the perfect squares? 1 plus 1/4 plus 1/9 plus 1/16. What does that sum equal? Pi squared over 6, finite number. This is your P series from calculus. I hate the name. Number theorists hate the name because it has nothing to do with primes. Notation is sadly with us. Okay? This tells you that there are far more primes than perfect squares. So many primes that the sum of their reciprocals diverges. Right? So one way to show a set is infinite is to show that the sum of the elements or the reciprocal of the elements, something along those lines, diverges.
Couldn't you just have them the same number but like grouping earlier? Is that possible or not?
So I mean, we're comparing different sizes of infinity. And so what we're doing, but I mean, so what you often do is you look at what fraction of your numbers up to x are in your set. So what fraction of numbers up to x are perfect squares? We have square root of x squares, essentially. So the fraction of numbers that are perfect squares would be square root of x over x, which is 1 over square root of x. Or a better way of saying it is the number of perfect squares is going to be square root of x over x. The primes is x over log x. So this is the number of perfect squares up to x. This is the number of primes up to x. Far more primes than perfect squares. OK, so in terms of proving Chebyshev, I'm not going to go through all of the calculations. I want to just handle one interesting part of it. And so there was a sum that I really liked that came into play. And the sum was the following. We got pi of x minus pi of x halves was less than equal to x log of 2 over the log of x halves plus some constant of size 1. And eventually, after some analysis, we got pi of x was less than equal to 3 plus 2, the sum k less than equal to k naught of x over 2 to the k over the log of x divided by 2 to the k. And here, k naught is such that k naught is the floor of the log of x base 2. And it is not log today. OK. So the difficult part in Chebyshev is we've got to get a good upper bound for the number of primes. We have to get a good lower bound. This is, again, breaking things up into dyadic intervals. So this is a huge idea, dyadic intervals. And so we're looking at things, x halves, union, x halves, x fourths, union, x fourths, x eighths, union, and so on and so on and so on. And we're breaking the analysis up into each one of these. So if I have an estimate like this, all I then do is I keep replacing x with x over 2. And then x over 4, x over 8, et cetera, et cetera, et cetera. And what kind of sum are we going to get?
Geometric.
Not geometric. So we'll have pi of x minus pi of x halves. Pi of x halves minus pi of x was, it's going to be a telescoping sum. And you'll see everything will cancel except for pi of x and maybe pi of 1. So I'm going to assume you can count how many primes are at most 1. All right, that's not so bad. We keep doing the telescoping sum so many times, it doesn't really matter. And then that will give us a really good estimate for pi of x. So now when we do this, that's why we only have to do finitely many k. What's going to happen if we start doing too many k? Well, if we do too many k, the 2 to the k is going to be larger than x. And you'll be counting how many primes are at most 1/4, how many primes are at most 1/3. Yeah, this is ridiculous. You would never try to estimate a quantity like that using an involved method. Just calculate directly how many primes are less than 1/4. So you'll basically go for k up to about the log of x base 2. Do the last few values of k really matter when k is huge? No, when k is huge, this logarithm is maybe log of maybe 2, 3, 4, 5, some small number like that. And this is like 2, 3, 4, 5 up here. We're talking about a contribution that's maybe at most 10. So the last few k's don't really contribute. So we want to get an understanding of this sum. And this is why I wanted to concentrate on this part rather than all the different details in this chapter. How do you understand a sum like this? We have two competing influences. What makes you think that this sum could be large? So why might this sum be large?
K not likely very large?
Well, but we've said the last few terms are not going to really add that much. So which terms are going to be very large here? So you've got these summons. When k is small, why are the terms going to be large when k is small?
Because the x over log x goes up as you go out, and k is small makes the argument bigger.
So when k is small, this becomes x over 2 to the k is going to be large. But then we're dividing by the log of a large number. So when k is small, the numerator is very large, but we're also dividing by something that's essentially log of x. What happens when k becomes very large? Now we're no longer dividing by something that's large, because if k is very large, x over 2 to the k is going to become a lot smaller. So that's going to make the terms larger, but of course if k is large, what happens to the numerator? Small. So there's competing influences. When k is large, the denominator is going to be the log of a small number, so you're not going to divide by as much. That's going to help, but then the numerator is much, much smaller. Which do you think is going to contribute more, small k or large k? To the overall sum. Small k. You know, the fact that you're taking more and more powers of x up here is really bad. You know, that you're decreasing x by so much. If you want to really get a feel of something like this, try breaking the sum up to k less than or equal to like log x. Something like that.
I mean, you know that u over log u increases as u gets bigger. And if k is smaller, it means u get bigger.
But then you have more terms where k is larger. So maybe those more terms will start to contribute. Now the nice thing is if you wanted to just trivially estimate this, you could trivially estimate it by saying I have log x terms. Each term is at least x over log x. So if I multiply them together, I have at most on the order of x for the number of primes. That's going to be a horrible estimate. Right? So the question is, how do you want to break something like this up? One thing is to try to figure out where is a natural place to split the k. If you take k to be like log x, why might that be good? Or maybe log 2 of x? Well, then that would give me like an x over log x term. That's essentially where I think the transition might be happening. And so when you have terms like this, it's always a question of where do you want to split it. So I think I chose to split it by a little bit different way rather than doing logs. So I choose to split at k equals the log base 2 of x to the 1/10. That's where I chose to make the split. Why do you think this is a good place to split? So what's good about splitting over here? Let's look at what's going on. We have x over 2 to the k log of x over 2 to the k. And now we want maybe to look at k less than or equal to the log base 2 of x to the 1/10. In this range over here, what's going to happen? What can you say about the log of x over 2 to the k? Do you think I want upper bounds or lower bounds? So I'm trying to show pi of x less than or equal to this. I want to understand this sum.
In the range of k less than,
Yeah.
you want an upper bound.
I think I want a low bound because this is in the denominator.
Okay.
I've got the log of x over 2 to the k in the denominator. So let's see what we can say about this. Well, if I want a lower bound for this,
Yeah.
the lower bound is when k is as large as possible. And that's going to be greater than or equal to the log of x divided by x to the 1/10. What's x divided by x to the 1/10? X to the 9/10. This is 9/10 log of x. The important thing to note is we really haven't seen that much change in terms of the size of this term. Even though we're going a huge amount, we're going 1/10 log of x. We're going a positive percentage of the entire interval we need to look at. But the denominator does not change significantly in here. When I take k equals 1, I have the log of x. When I take k equals the log of x to the 1/10, I get 9/10 log of x. The denominator essentially has not changed at all in this range. This is a little surprising if you haven't done calculations like this before. Because my whole interval of k is going from 1 all the way up to the log of x base 2. We're moving up 1/10 of the way.
However, then all of a sudden the numerator isn't going to be growing linearly anymore.
That's fine. I mean, the numerator is going to be damn small by the time we get up to here.
Well, I know that's, well, all right.
And that's why we're going to win on the next part. So what I'm trying to do is I'm trying to break it up. In this region, the denominator doesn't really change. I'm going to have a geometric sum that I can evaluate. And this will now give me the sum of k less than or equal to the log of x to the 1/10 base 2 of x over 2 to the k over the log of x over 2 to the k is going to be less than or equal to the sum k less than or equal to the log base 2 of x over 2 to the k. No, sorry, log 2 of x to the 1/10. And now I've got a 9/10 here, so I'll have like a 10/9, I think. And I'll have an x over log of x times 1 over 2 to the k. So how would I handle something like this? What would I do for this piece over here? How would I handle this sum?
Don't worry about the x and just do a geometric.
Yeah, just do a geometric series. And in fact, if I wanted to, I could even make k less than or equal to infinity. It's only going to change by a constant, right? I've got the x over log x term. So in this range for these k, now, as k gets very large, are my terms really of size x over log x? As k gets close to the log of x to the 1/10, are my terms really as large as x over log x? So what happens when I put over here k equals the log of x to the 1/10? I'll get x over x to the 1/10, which is x to the 9/10. I'm greatly overestimating the contribution of the last few terms. But I'm trying to show a bound of size x over log x. These terms are contributing x to the 9/10. They're negligible. It doesn't matter. Most of the contribution is going to come from the first few terms. I will maybe have my constant off by a factor of 4 or 10, something like that. Doesn't really matter. And it makes the calculation significantly easier. So this is a big part of analytic number theory, is trying to figure out how to do estimates like this. Trying to break things up into different regions where you have good control. And if I break it up like this, I have really good control. The denominators are not changing that much. That's the advantage of the logarithm. The numerators, yes, they're greatly changing. I'm making mistakes when I replace it. Who cares? Okay, any questions about this part? All right, what about the next part? Now we need to look at the larger values of k. So if we try to do the larger values of k, so now we want k greater than or equal to the log of x to the 1/10. What do you think is going to happen in that range? So now we have x over 2 to the k over the log of x over 2 to the k. There's lots of ways you can do the estimation here. So lots of different things will work. Which is going to be the largest term? So this is going to be less than or equal to x to the 9/10 over, now I've got to be careful here, because unfortunately, as k gets larger, that's going to make this smaller. Maybe log of 2. Because I know k doesn't go all the way off to infinity. Right? We stop when x over 2 to the k is, say, 2. So I'm approximating the numerator one way, the denominator another way. This is another common technique. Where's the numerator worse? Where's the denominator worse? Take them together. Each of the terms is at most x to the 9/10 over log of 2. How many terms do we have?
Or log 2 to x minus log.
No!
Okay, just lower log.
Yes.
Lower log to x.
Have at most log 2 of x terms. Right? Let's not worry about subtracting off something. Let's overestimate a little bit. So the sum over k greater than or equal to, we'll have k goes from the log base 2 of x to the 1/10 to k naught of x over 2 to the k over the log of x over 2 to the k. That's going to be less than or equal to the log base 2 of x times x to the 9/10 over the log of 2. And that'll be less than or equal to x to the 9/10 log base 2 of x with some constant. Okay? And that's going to finish the analysis. And so that will allow us to show that this sum over here is less than or equal to some constant x over log x. Right? So there's a lot going on in this analysis. When we have a sum like this, we want to figure out where do we want to break it. If you really cared about your error terms, if you really cared about the analysis, if you really cared about the constants, do you think 1/10 is the optimal place to break? More than probably. Right? Where the hell is a 1/10 coming from in this problem? Right? I can't see any place where a 10 is coming into play. I deliberately chose that number so that it would not be good. Okay? The question becomes, where is the optimal place to break it? If you really want to test your knowledge, if you really want to test how well you've processed this, try to figure out where should you break things so that the two terms are of equal size. So my first term is of size x over log x. The other term is of size x to the 9/10 log x. There's a big difference in relative sizes. And because of the big difference in relative sizes, this is almost surely not the optimal. You might, in a lot of these problems, you want to optimize in such that both terms are, say, comparable size. And so we probably don't want to go all the way down to x to the log of x to the 1/10. In fact, if we go to x to the c for any c less than 1, that's probably too far. Because if we go that far, then the other term is going to have a power savings. It's going to be, x to the 1 minus c times log of x. So this method is fundamentally not going to give you the best split between the two terms. Do we care? No. We're just trying to get some bound of the form x over log x. Maybe we want to go to log x. Or maybe log x, then maybe take the square of that. Some games to play. Yes?
So our bound's not really close to as good as x over log x, right?
For the last one?
Yeah.
Well, this is a much better bound than x over log x. This is much smaller. This is x to the 9/10. We can write this as x over log x times log base 2 of x divided by x to the 1/10. So this is significantly smaller. So we have a lot more control over here than we need. The problem was it came at a cost. It came at a worse estimate over here. So if we're trying to figure out the optimal way to split things, almost surely splitting it at the log of x to a power is not the right way to go. So this opens up an interesting question. Where should you split it so that the two terms are equal? Is it log x? Is it log the square of log of x? So I'm not going to go into all those details. I will just leave that as something to ponder. Yes?
So the fact that the denominator doesn't change that much, and the first time we estimated on the one hand is good for estimating, but on the other hand it isn't good if we wanted this power savings or something like that, or if we saw the second one.
Or if we cared about the true value of the constant. And so in the estimation we're doing over here, we're replacing the denominator with something that's essentially constant. Now, is the denominator changing significantly? It's going from log of x to 9/10 the log of x. That's not a huge change. And then we can approximate this thing exactly by using a geometric series. So in terms of trying to understand the true value of the sum, the amount of error we're making over here is on the order of a factor of 10/9 in terms of how big our error is. All right, so we might inflate our constant by a factor of 10/9. So that's insignificant, right? We're talking about being off by on the order of magnitude of about 10%. So in terms of trying to estimate the true value of the constant, being off by a factor of 10% is nothing. So here's the thing. Is it really worth trying to optimize the two for a 10% gain? There has to be a damn good reason to need that 10%. If we were trying to do Bertrand's postulate, if A and B were too far apart, then we would not have that there were primes in the interval. And then we wouldn't have that there are many primes in the interval. And then in a situation like that, then yes, then maybe we would have to refine our arguments to get to that point. Number theorists, like mathematicians in general, we are lazy. We are as lazy as we can get away with. And for a lot of the applications, something like this is more than enough. The difficulty is when you need more. Is if you need to figure out exactly what is the smallest constant to get x over log x. If you're trying to prove the prime number theorem, you want to get that constant to be 1. And then anything above 1 is horrible. We expect the fluctuations about x over log x to be roughly on the scale of square root of x. So we expect them to be much, much smaller than x over log x. So if we replace the constant 1 x over log x with 1.00001 x over log x, that's far more than we believe the truth is. So again, I just want you to get a sense of how you do calculations like this, why calculations like this matter. Okay? The next one, and if you want, I'm happy to do this in class on Monday. No, I'm sorry, I won't do it in class on Monday. Monday is a holiday, right? Monday is reading period. So on Wednesday, if you want, one of the integrals that came up in the chapter was integrating from 2 to x of du u du over log squared u, I think. And we wanted to figure out how big is this. And one of the ways we analyze this is I like to break it up like this. So we want to show that this is roughly of size x over log squared of x times some constant. The problem is, as u gets very, very large, we divide by log squared. When u is very small, we divide by a constant. That's a huge change to go from a constant to log squared of x. If we break it up like this, from 2 to square root of x, there's going to be major changes in the size of this. But how large is my number here? Oh, yeah, maybe I just want, I don't know if I want the u there. Oh, no, I don't want the u. I want the u to cancel. Yeah. So if I go up to square root of x, the denominator changes significantly, but it's over something of size square root of x. So this part over here would be less than equal to the square root of x, or square root of x minus 2 if you want to be really pedantic, times 1 over log squared of 2. That's insignificant relative to the main term. If I now look at this interval over here, the size of this is about x minus square root of x. I call it x. The square root of x doesn't really matter. And now when I want to understand here, if I go from square root of x, that's going to give me the log squared of square root of x. That's 1/2 log x. That's 1/4. And if I put in x, it's just log squared of x. So it's going to differ by a factor of 4. So this is going to be from like 1/4 x over log squared x to essentially x over log squared of x. Something all like that. Or maybe the 4 was the other way. If I put it in like that, I've definitely made myself safe. And this is how you handle integrals like this. And this one you can do a much better job splitting up than this. So if people want, I'm happy to do this calculation in detail. And the question is square root of x the right place to split this? What do you think? Hell no, right? This is square root of x. This is of size x over log squared x. So then the question becomes, where do you want to split it? You probably want to have this go all the way almost to x. Maybe x over log squared x. Maybe someplace around that is where you should be splitting things. So that's another thing we can talk about on Wednesday if people want. If you do, email me and I will include that in the lecture. If not, I'm going to start going in chapter 3 in detail. All right.